Well, good morning. So today we're going to be finishing chapter 4. If you remember, that's about UV vis, so visible and ultraviolet molecular absorption spectroscopy. And remember that UV vis light is the one that, before we get into that. So remember I told you for all of these instrument chapters, we'll always be looking at the instrument. So we looked at that the last couple times, Beer's law and the components, what's inside the instrument, the types. We'll look at the theory. And last time we looked at molar absorptivities, okay, what they are and what the size of the numbers means. Today we'll be looking at the types of transitions and a few factors that affect where your peak maximum is. And then we'll look at applications and how we actually use this method. Okay, so UV vis light is the one that has enough energy to excite electronic transitions. And these transitions are always going to be the outermost electrons. They're called bonding electrons, valence electrons. Okay, and last time we said there's actually 3 different types of these electronic transitions that are common in UV vis spectroscopy. So the first one is what we'll spend most of our time on because it's the most common use, and that's the sigma, pi, and n electrons that are in organic molecules. Okay, and then we'll look very quickly at D and F electrons. These would be in inorganic molecules. And then charge transfer is usually a metal, ion, and then some organic complex that combine. Okay, and again, all of these transitions are electronic transitions that involve the valence electrons. Okay, so right at the end of class last time, we said, we just kind of reviewed this terms, the N sigma and N electrons. You should have studied these in another class. And so all organic molecules have these kinds of electrons. So the sigma, that's the single bond. So any organic compound has single bonds. Those are called sigma bonds. The double and triple bonds are called pi bonds. So those are the pi electrons, the electrons in those double and triple bonds. And then the N electrons are the lone pairs. So any of these atoms listed down here that would have lone pairs. So a quick example, this molecule, we know the carbon-oxygen bond, there's a single bond, that'd be the sigma electrons. And then the double bond, the second bond would be pi electrons. And then the N electrons we would see here on the oxygen, those lone pair. Okay, so we can actually take these different kinds of electrons that are in an organic molecule and make an energy level diagram. So the sigma electrons always have the lowest energy, and then usually the pi, and then the N, and then we have a couple of excited state, pi star and sigma star. So there are 4 kinds of transitions that we talk about in the UV vis. So the first is the sigma to sigma star, and notice these have a lot of energy, which means very short wavelengths. And their molar absorptivities can be fairly small to quite large numbers. Okay, remember 10,000 is a big number for molar absorptivity. All right, next we have the pi to pi star. Now these are in our key range, that 200 to 700. That's kind of the key UV vis range that we want to look at. And notice molar absorptivities are pretty big, 1,000 to 10,000 for these pi to pi star. Okay, then we can also have a N to sigma star. These are also short wavelength, high energy, and fairly low molar absorptivities. And then finally, there's the N to pi star. And these also, notice, are in that key UV vis range, 200 to 700. notice their molar absorptivities are quite small. Okay, so these would be those forbidden transitions. But remember, forbidden just means they are less strong. They don't occur as frequently, but they're still going to be very useful for us. Okay, so taking a closer look at these four types of transition. Okay, the sigma to sigma star, these are in the far UV, and so they're not easy to measure. So these are not going to be useful for us. So we're not going to talk about these again. Okay, so we're done with those. The N to sigma star. These are in compounds that have something with a lone pair and single bond. And most of these are also down in the low UV, the far UV, 150 to 250. So these also are not very useful for us. There are a few that are in the normal UV where we can measure them, and this table shows you. So notice, remember, normal UV is 200 to 400. So notice, there's a few of these that are in regions we could measure, but overall, again, these are not that useful for us. So we're not going to talk about these again either. So really, you only have to remember two kinds of transitions for organic molecules, okay? Because these are the ones that are in the normal UV and the visible, those ones from 200 to 700. So the important ones are going to be the pi to pi star and the N to pi star. Now, notice both of these have this pi star. Pi, remember, means there's a double bond or a triple bond. So all of these molecules are molecules that have double bonds or triple bonds. Okay, that's what you need to have that pi star excited state. All right, so the pi to pi star, as I already said, the absorptivities are pretty high. So these are going to be pretty strong transitions. Okay, then we also have the N to pi star. So those molecules, again, they have to have a double bond because of the pi star. But notice the N. Okay, the N means lone pairs. So these are all going to be molecules that have something with a lone pair of electron. Things like nitrogen, oxygen, sulfur, chlorine, those kinds of atoms. And again, these molar absorptivities are much smaller. So these are going to be weaker transitions. This table is in your book, and it just shows you kind of some typical values for a few transitions. So notice the alkene, the carbon double bond, usually is around 177 nanometers. That's a pi to pi star transition. The triple bond, pi to pi star, that's at 178 nanometers. So kind of low UV. Most of the rest of these are N to pi star, so they're things that have a double bond and then something with those lone pair of electrons. And they give you approximate wavelengths for those. Now, you don't need to remember any of these numbers. In fact, we'll see later that these numbers change under different conditions. Okay? But just so you can see, there are tables that give you an idea of where some of these different transitions occur. Okay, so far we've learned there are two important transitions for organic molecules that we need to know. Okay, there's four, but we only need to know two. Pi to pi star and N to pi star. So what you should know is you should know, okay, molar absorptivity. Which one is bigger? Which one is smaller? Okay, well, remember, pi to pi star, bigger numbers. Those were 1,000 to 10,000. N to pi star, smaller, 10 to 100. Okay, you should know about the energy of the transition. So notice the pi to pi star is here, that's this one, and the N to pi star is here. So notice the pi to pi star is a bigger energy, and the N to pi star is smaller energy. Now, if the energy is bigger, remember that means the wavelength is shorter. Okay, so pi to pi star will have shorter wavelengths, n to pi star will have longer wavelengths. Now, these are the normal trends. There are some exceptions. There are some times when these trends are not true, but in general, this is how you can compare pi to pi star and n to pi star. Okay, next we want to look at the shape of the UV-Vis spectra. And we've already looked at this a little bit in chapter 2, but remember these peaks are these very broad peaks. Now, when we looked at this energy diagram, notice it's just showing us these lines, from one line to the next line. Okay, but really that's not the case. Remember, what we really have is we have all those vibrational levels. And then on top of the vibrational levels, we have all those rotational levels. So when I absorb light, I can absorb up into any of these vibrational levels and into any of these rotational levels, which means that you get a very broad peak. And so UV-Vis spectra are always going to be broad peaks, okay, not lines, broad peaks. Also, the shape of these peaks will change depending on what your solvent is. So for example, the UV-Vis spectrum for this molecule right here, if it's in water, it's that big, broad peak. Now, for some molecules, not all, but for some, if you put them in a non-polar solvent, like hexane, okay, hexane is C6, that carbon C6H14. Sometimes you'll get spectrum that look like this. And what you're seeing here are actually the vibrations. You're seeing absorption into different vibrational levels. Okay, usually we don't see the vibrational levels, but for some compounds in non-polar compounds, you'll see this. This is called vibrational structure. And then if you actually get the molecule in the gas phase, you'll actually see something that looks like this. You'll see vibration and rotational levels. Okay, but we won't be considering things in the gas. Most common will be solutions. And again, most absorption spectra are just going to be these broad peaks with no structure. Okay, now we want to talk a little bit about choosing the solvent and what's important for the solvent that I'm going to put my analyte in. So the first thing is the solute has to be completely soluble. Okay, now what if it's not completely soluble? Well, you're going to have your cuvette and you have your solution. And if this is not soluble, then you're actually going to have particles in that solution. And when the light goes through, it will hit those particles and scatter. And you won't get a good absorbance measurement. Okay, so solute has to be soluble. Okay, second thing you have to consider is you have to consider that the solvents, okay, most solvents are organic compounds, and so they absorb light. And for example, acetone, which has this structure as a common solvent, this is the absorption spectra of acetone. Now, if you're trying to measure your compound in acetone, then you can't measure absorbance less than 330 because now the solvent absorbs. Okay, so we call this the cutoff value. Okay, that's the highest value you can measure before the solvent interferes with your measurement. And there's actually tables that show you the cutoff values. Notice acetone is quite bad. It's one of the worst. But notice there are some that don't start to absorb until very low. And actually in real life, the most commonly used solvents are water, because it has a very low cutoff, and then hexane, which is quite nonpolar, and then ethanol. So these three are probably the most common solvents. Methanol is pretty common too, but a lot of these are used depending. Sometimes something won't dissolve in one of these and you pick a different solvent. But again, you have to know where does your solvent start to absorb. Okay, the third thing you have to consider is how does the solvent affect your spectrum? Okay, we've already seen that the solvent can change the way it looks. You know, if we go from water to hexane, we go from this broad peak to having vibrational structure. Okay, so polar solvents tend to give you the broad peaks with no vibrational structure. Non-polar solvents will give you this fine structure. We actually kind of see the absorption into those vibrational levels. The other thing that different solvents will do is it can shift the band position. So, you know, we could find out for this one that, you know, right here is lambda max. But if we change the solvent, we can actually sometimes move the position of that band. We can move lambda max. So we want to look at how do we do that. So before we look at how do we move that, we have to look at some vocabulary. So the first vocabulary is this word chromophore. And so this part of the word chromo means color. So the chromophore is actually the part of the molecule that absorbs the light. Okay, that part of the molecule that's responsible for your absorption band. That's called the chromophore. And so that table that I showed you before, you know, this chromophore is an alkene. It's this C double bond C. And then it told us, you know, this is about where this absorbs, about 177. Carbonyl, so this right here, that's is the chromophore. That's the part of the molecule that absorbs. Okay, so you can look at tables and get approximate wavelengths for these. But those numbers, okay, these lambda maxes, they change if you change the solvent. Okay, so notice in this table for each of these, it tells us what solvent they used. If you change the solvent, this lambda max will change. Also, lambda max will change if there's interactions between the molecules. You know, especially if you have a high concentration and the molecules start interacting with each other, or if the molecules interact with the solvent, that will shift the lambda max. Okay, so when we talk about lambda max changing, there are some terms that we use. So if lambda max shifts to a longer wavelength, okay, remember longer wavelength is a lower energy, that's called a red shift. Now red shift is the informal name. The formal name is bathchromic. Okay, now if it shifts to a shorter wavelength, higher energy, that's called a blue shift. And the formal name is hypsochromic shift. Now I'm just going to use red shift and blue shift. Okay, that's easier to remember, understand. And remember, red shift to longer wavelengths, blue shift, shorter wavelengths. But if you're ever reading a paper or a book and they're using these other terms, bathchromic and hypsochromic, and you can't remember, oh, is that the red shift or the blue shift? The easy way to remember is, you know, think of the bathchromic, okay, the word bath here. Now, if you're taking a bath, would you like to use hot water or cold water? Well, of course, hot water. We don't want to take a bath in the cold water, especially with winter coming. And remember, when we look at the faucets, there's that red and blue. Red always stands for hot, blue, cold. So the red shift is the bathchromic, and then blue shift is the other one. So that's how you can remember that. Two other terms we use are hyperchromic and hypo. So hyper means to increase the intensity, hypo, decrease the intensity. Now, these two prefixes are actually common in English. Hyper means over or in excess, and hypo means under or lacking. So sometimes you will see hyper and hypo used with other words. So like your thyroid that produces things for your body. If it produces too much, it's overactive, they call it hyperthyroidism. If it produces too little, that's hypo. So these words are actually kind of useful to know their meaning because you'll see them with other words in English. Okay, but we're concerned about spectroscopy. So this diagram now just shows you red shift to longer wavelength, blue shift to shorter wavelength. Hyperchromic intensity increases, hypochromic intensity decreases. Okay, now we have the vocabulary. So we want to look at, okay, what causes these red shifts and these blue shifts? So first we'll look at one cause of a red shift. Okay, remember that's the shift to a longer wavelength. So it turns out that a pi to pi star transition, if you change from a non-polar solvent to a polar solvent, there will be a red shift in the peak. Now, the reason is when you put that molecule into a polar solvent, okay, it lowers the energy, and it lowers the energy of both the pi state and the pi star state. So in the non-polar solvent, this is the energy you need for the transition. And notice the pi star energy drops more than the pi. Okay, so this is the energy that you need in a polar solvent. And notice that energy is much less. And the reason these energies drop is because you get interactions between the solvent and your molecule. You get dipole-dipole interactions and hydrogen bonding. And that's why these energies change. Okay, so what that means is that pi to pi star transition goes to a lower energy in polar solvents. And remember, lower energy, that means longer wavelength or a red shift. Now, these shifts are pretty small, only about 5 nanometers, okay? But it is a shift of that lambda max, about 5 nanometers red. Now, what about the other transition, the N to pi star? Well, that's also going to be affected because it's that same pi star energy that's going to drop, but it turns out that the N electrons, the N orbital, is affected even more by the polar solvent. Okay, the pi star was affected quite a lot, we see here, compared to pi, but the N is affected even more. So notice here, this is the non-polar solvent and the polar solvent. So notice the pi star drops, but the N really drops in energy. Okay, so notice what happens to the energy of the transition. So in the non-polar solvent, smaller energy. In the polar solvent, the energy gets much bigger. Okay, so increases significantly, and if the energy gets higher, that means the wavelength gets shorter. So you're going to get a blue shift. And these shifts are much bigger. These are about 25 to 50 nanometers. So this is a much larger effect. You can also get blue shifts if you have a solvent that doesn't hydrogen bond but has lone pairs of electrons. It will cause the same kind of shift in your molecule. Okay, so if we change the solvent, we go from a non-polar solvent like hexane to a polar solvent like water or ethanol. Okay, we've seen that both the N to pi star and pi to pi star have small red shifts. Okay, but the N to pi has this large blue shift on top of that. So for the N to pi star, the blue shift is the one that prevails, is most important, okay, is the main effect. Okay, so going back to this table where we were comparing pi to pi star and N to pi star. Okay, now in polar solvents. So pi to pi star transitions, they will, when you go from nonpolar to polar, they will redshift. N to pi star, when you go from nonpolar to polar, they will blue shift. Okay, and the red shift is fairly small. The blue shift is much bigger. Okay, now this is an important property to know. Okay, so we compared the molar absorptivity and the energy and the wavelength, and I said usually these are true. There are some molecules where this is different. But these shifts, these are always true. Okay, always pi to pi star, red shifts in a more polar solvent, N to pi star, blue shifts in a more polar solvent. Okay, so here I have a compound that is measured in hexane. And notice that it has two peaks, which means that it has two transitions. And we know that one of these is pi to pi star. The other one is N to pi star. Okay, now, based on what we know, which peak do you think is pi to pi star? And which one is N to pi star? Okay, well, remember, pi to pi star, larger molar absorptivity. That means the peak should be higher. Larger energy, shorter wavelength. Okay, so we would guess that this first peak should be pi to pi star. It's higher intensity, shorter wavelength. And this one should be N to pi star. Okay, but remember I said that those are usually true, but not always. So how can we prove that this peak is pi to pi star and this one is N to pi star? Well, what we just looked at, we can change the solvent. Okay, so notice this is non-polar, so we change this to a polar solvent and get the absorption spectra. So same compound now in ethanol. And notice this peak red shifted and the other peak blue shifted. So now we know for sure this one's pi to pi star, this one's N to pi star. Notice also the intensities changed for these peaks. That also can happen when you change the solvent. Sometimes you will increase the intensity or decrease the intensity of the peak. Okay, so that's the first thing that can affect peak position is polar versus non-polar solvent. The next thing we want to look at is conjugation. So conjugation is when you have bonds that alternate single, double, single, double, single, double, like you see up here, over more than two atoms. So when you have more of these double bonds, what happens is the pi to pi star energy starts getting closer and closer together. So for example, if I just have one double bond, okay, here's my pi to pi star energy. But if I have two double bonds, each of those has an energy level, and those energies will be slightly different. Okay, now if I have three double bonds, okay, again, each has a slightly different energy level, like this. If I have four, okay, now we have four of these. And you can see the more of these I have, the smaller that transition gets. Okay, smaller transition, smaller energy, longer wavelength. So you're going to see the maximum shift to longer wavelengths. And so notice here I've got 3 sets of these double bonds versus 4 versus 5, and the absorption maximum get more and more red the more double bonds you have. Also, the intensity increases as you get more of these. Okay, so that's a conjugation effect. Will also cause more conjugation means more redshift. Here's a table that shows you an example of this. So here's a molecule with only one double bond, and notice its lambda max is 184. Okay, now we have one with 2 double bonds, but these are not conjugated. They're not next to each other. So these two have about the same lambda max. All right, now we have a conjugated system, and notice redshift. Here, 3 double bonds, even bigger redshift. Another example, here's a ketone. So here's its pi to pi star transition. And then here's unconjugated. Now conjugated. So again, notice this redshifts. Okay, another example. Here's 3 molecules. All of them have absorptions around 270. Okay, and then there's this guy. This is its structure. Notice this is very, very conjugated molecule. And notice its absorption max all the way out at 450. So very redshifted. Okay, so that's the conjugation effect. The more conjugation, the more something is redshifted. All right, finally, we want to look at aromatic systems. And we'll start with benzene. Benzene actually has 3 different pi to pi star transitions. And they give them names. So one of them is called the E1 band. Now notice this is in the far UV. It's a very strong band, but we cannot easily measure this. So this is not very useful for us. Okay, but the other 2 we can get to, the E2 band and what they call the B band. And typically this B band will actually be very, it'll have some of that vibrational fine structure if it's in the vapor phase or even in some solvents. And then as you get it in solutions, especially more polar solutions, then it gets broadened out. So this is what the absorption spectra of benzene looks like. So notice this is that E2 band and then the, E1 and then E2. This is the B band. And again, quite often it's going to have this vibrational structure. In some solvents, you may get that broadened out so that you don't see those peaks. Okay, so here's a table showing benzene with its E2 band and its B band. And then notice they have a bunch of other compounds. All of these are benzene rings with other things on them. So what we're going to see is that putting substitutions on the ring, okay, putting anything on the ring strongly affects those bands, all 3 bands. So there's another term they use. It's called an oxyochrome. So this is a functional group that does not absorb, but it affects the absorption of the chromophore. So remember, the chromophore here for these benzene rings are those carbon-carbon bonds. But when we put something on the benzene ring, it's going to affect the absorption of that carbon-carbon bond. So there are a lot of things that affect the absorption. We'll just look at 2. So if you put either OH or NH2 on benzene, it will affect the absorption. So we say they're oxychromic. That means they affect the absorption bands of benzene. And the reason they do that is because both of these have at least 1 lone pair of electrons. So, nitrogen has its lone pair, oxygen has a couple lone pair, and these lone pair can interact with the pi electrons, and it lowers the energy of the pi star state. So you're going to wind up with a red shift. Okay, so going back to this table, here's benzene, and here we put OH on it. So notice the E2 band red shifts from 204 to 211. The B band from 256 to 270. So both bands are affected. NH2, we put that on the ring. Again, you see a red shift of both peaks. Now, notice there are a lot of things we can put on the ring that will affect the absorption, but the only 2 you need to remember are OH and NH2. Okay, what about conjugation of aromatic systems? Well, we already saw before conjugation of straight chain. The more conjugated, the more red shifted it gets. Okay, also rings. The more conjugated, the more redshift. So notice we put two rings together, we get this spectrum. 3 redshifts, 4 redshifts, even more. Okay, by the way, these two rings together, that's this compound right here, naphthalene. Okay, and you can see, again, both of those peaks are redshifted because of the conjugation. Okay, so for organic molecules, okay, what do you need to know? Okay, we talked about these 4 kinds of transitions, but we said really the only 2 that are commonly used, okay, the 2 that are most important are pi to pi star and n to pi star. So you should know these 2 transitions. Okay, you should know that this one has larger molar absorptivities, larger energies. This one, lower molar absorptivities and lower energies. Okay, then you should also know that in polar solvents, pi to pi star will redshift, okay, when you go from nonpolar to polar. N to pi star will blue shift. Okay, the red shifts are fairly small, the blue shifts are fairly large. Okay, you should also know conjugation causes redshift. And aromatic rings, okay, putting OH or NH2 on the ring causes a redshift. Conjugation of the ring causes a redshift. Okay, so this is what you need to know for pi, sigma, and n transitions in UV Vis. Okay, so that's not too much. All right, are there any questions about that? Okay, the other kinds of transitions, these will be much quicker. We're just going to look very quickly at what this set means. The next type are the D and F electrons. So this is what we use in inorganic molecules. So the F electrons, these will be compounds or even the atoms that contain any of these elements. And the D electrons are the transition metals, so containing any of these. And both D and F electrons absorb UV Vis light. In fact, if you look at these are all actually visible light, not UV. So notice the D electrons have kind of these broad peaks in the visible region. The F electrons, they absorb with very sharp peaks, also in the visible region. Often you will see compounds that have these different metals in them, and they are often brightly colored, okay, because of these absorptions. One thing to note, notice these plots are not absorbance versus wavelength, but they're molar absorptivity. And notice the molar absorptivities for most of these are quite small. Okay, that means most of these transitions are pretty weak transitions, but we can still measure them. Okay, so you can measure inorganic compounds that have D or F electrons with visible light. Okay, and then the last one is charge transfer absorption. So this is usually where you take a metal ion that does not absorb strongly and you complex it with a compound. And the compound will form a new complex that absorbs very strongly. They show you 3 examples here. So notice here, iron 3 is combining with, this is called thiocyanate, and it forms this compound, and this compound is a bright, deep red color, a very strong absorption spectra. And often the absorption spectra of these charge transfer complexes are quite large. Another one is taking iron and combining it with phenanthrene. That's this compound. Again, you get something that absorbs very strongly. And then you can take iodine, combine it with a starch molecule, and again, get something that absorbs very strongly. So those are charge transfer absorptions. And this is a way to take something that does not absorb strongly and you combine it with something that now forms something that absorbs quite strongly. Okay, so we have now finished part 1. We talked about everything in part 2. We looked at the type of transitions and the factors that affect the band positions. So that just leaves us with the applications and the use for this method. Okay, so we talked about the first chapter, actually the first day, that analytical chemistry answers these 2 questions. What is it? How much is there? And we said what is it is qualitative analysis. How much is there is quantitative analysis. So we said anytime we look at a method, we always want to know, does the method give me qualitative information? Does it give me quantitative information? Okay, so now we want to ask that question. Does this method, UV-Vis absorption, give me qualitative information? Okay, and the answer is yes, but it's limited. Okay, remember the number of absorption maximum are pretty few. And many compounds have spectra that look very much the same. You know, for example, this top one and this bottom one, if you just had the spectrum on the same scale, you know, they look pretty much the same. So often it's very hard to identify something if this is all you have. You really cannot say for sure, oh, this is caffeine or this is acetone. So it's not a powerful qualitative method. Okay, it is useful to detect a few functional groups. Okay, for example, if you have a weak absorption band from 280 to 290 and it blue shifts when the solvent polarity increases, that tells you it has a carbonyl group. Okay, so here's a band that blue shifts in a more polar solvent. What kind of transition is that? Blue shifts, more polar solvent. Is that pi to pi star or N to pi star? Okay, it is N to pi star. Okay, remember N to pi star, blue shifts. And notice this carbonyl, double bond, and lone pairs. Okay, so a weak band, 280 to 290, that shifts, tells you your molecule has a carbonyl group. If you have a weak band around 260 that has vibrational fine structure, okay, so you have something that looks like this in your absorption spectra, that tells you you have an aromatic ring, that benzene ring. There are some rules you can actually use to predict the absorption maximum of dienes and polyenes. So conjugated compounds, there are some rules that you can use to predict the absorption maximum. They're called Woodward's rules. They're not really used much anymore, so we won't look at them. But if you already kind of know that your compound is one of these dienes or polyenes, then this can be helpful. Okay, but in general, for qualitative analysis, okay, what is this? What is the structure? There are other techniques that are much, much more useful. There's one called IR, and one called NMR, and one called mass spec. These 3 methods are very powerful for determining structure of molecules. Now, we will not study these 3 methods in this class, but just so you know, there are some methods that give you some good qualitative information. Okay, so if this method is not very useful for qualitative analysis, it must be useful for quantitative analysis. Okay, to answer that question, how much is there? And in fact, this method is one of the most widely used methods for quantitative analysis. Okay, so we will take a break here, and then after the break, we will come back and look at how do we use this method for quantitative analysis. Okay, so 5 minutes. Okay, so let's see how do we use this very useful method for quantitative analysis. So if you're, before we get into how, what kind of molecules can we use this for? Well, as we've already seen, we can use it for both organic and inorganic. Okay, the organic is the N and pi and sigma electrons. The inorganic, D and F electrons. This method has pretty good sensitivity, so we can measure down to 10 to the minus 4 to minus 5 molar. Sometimes if the absorptivity is very big, we can go down to 10 to the minus 7. Pretty good selectivity, which means you don't have a lot of interferences. Okay? You don't have, remember, selectivity is being able to measure things in the presence of something else. Pretty good accuracy, usually about 1 to 3%. If you're careful, we can get it down to less than 1%. And it is a very easy method to use. At this point, you have finished the lab for this class. You've used this method. You know it's a quite simple method to use. Okay, so how do we use it? Usually you're going to be using a calibration curve. And if your analyte absorbs, then you just measure your analyte directly. You make the standards and make the calibration curve, and you can determine concentration. Now, sometimes your analyte does not absorb, or it absorbs very weakly. So then you can actually do some chemistry and make a complex that does absorb. So an example would be, again, that iron 2 combined with the 110 phenanthroline. It makes this complex, and this complex absorbs very strongly. Iron 2, very weakly. Okay, so now we can measure this complex and use that to determine how much iron 2 in this sample. Okay, so the procedures. So the first thing you should always do is measure your absorption spectra. Okay, so remember the absorption spectra is going to be absorbance versus wavelength. Okay, and then you're going to measure your absorption spectra. And then we're always going to select lambda max, okay, that maximum absorption. Now, why do we select lambda max? Okay, there are 2 reasons. Now, if you have been paying attention, you know that I have already asked this question several times. This is a very important question. It is one of the key points for this chapter, and I guarantee that on the next quiz and the final exam, maybe one, maybe both, you will see this question. Okay, what are 2 reasons we always use lambda max? Okay, so they are maximum sensitivity or maximum signal and good adherence to Beer's law, or it follows Beer's law. Okay, so you need to know, why do we always choose lambda max? All right, second thing, we need to be aware of anything that will affect my absorbance. That might be my solvent, my pH, my temperature, electrolytes in the solution, something that will interfere with the absorbance, like sulfates or phosphates. I need to be aware of all of those factors, and I need to control them. All right, third thing is you have to take very good care of your cell. So we've talked about the instrument. We talked about the source, and we talked about the monochromator and the sample holder and the detector. And when you did this experiment in the lab, you didn't see the source, you didn't see the monochromator, you didn't see the detector. The one thing that you touched, that you handled in the lab, was the cell. So it's very important that you take good care of the cell, that you know how to properly handle it. And then if you're doing a double beam instrument, remember you need to have 2 cells that have been matched. Okay, and so it's always important that you check your cells to make sure they're not damaged or have any problems or any scratches. And it's especially important to make sure your cells are clean. Okay, so if your cell has a big fingerprint on the middle of it, then that is going to affect your measurement. So the best way to clean them is actually to use methanol with lens paper to clean the surface. Okay, so there are several things that are also important for taking care of your cells and using your cells. So the first one, they have to be clean. Second one, most UV cells actually have 2 sides that are not transparent, and then they have 2 sides that are clear. So the light goes through here. So when you're grabbing that cell, your fingers always go on these 2 sides. Okay? You don't ever want to put your fingerprints on the surface where the light goes through. If you happen to have a cell that's clear on all 4 sides, then you should handle the cell up here by the corners so you don't get your fingerprints on it. If you're doing quantitative analysis, which you almost always are, you should take your solution and wash out the cell and dump that and then put new solution in so that you don't affect the concentration by anything that's been left in the cell from before. You don't ever want to use a strong acid or a strong base in these cells. Glass and quartz, it will scratch the surface, it will react. If you're using plastic cells, you need to make sure your solvent works with that plastic. Many organic solvents will attack plastics. You only want to use the correct cloth that your teacher gives you or that the maker of the cell gives you to clean them. You know, don't just ever grab any old thing that you have, a tissue from the lab, or, you know, use your shirt. You say, oh, my shirt's clean. No, you know, you could scratch it if there's any kind of dirt or the material's rough. So only use the proper cloths to clean them. And usually you want your cells dry, especially if you're doing quantitative analysis. You don't want to change the concentration, but you should never use a flame or a hot oven to dry the cell. That can damage them, cause them to break, maybe even change the path length. Okay, so those are some things you need to be aware of for the cells. Now let's talk a little bit about these matched cells for the double beam instruments. Okay, remember, these are 2 cells that have been matched, and one's going to be your reference and one's going to be your sample. But even though they've been matched, they're still not going to be exactly the same. There's going to be small differences in their absorption. So the first thing you have to do is to actually fill both cells with your solvent, and you run a baseline. Okay, so you're going to be running your baseline, and it should be very, very flat, but you know, might have a couple places where it's just a little bit off. And then you're going to store that as your baseline in your computer. And then, put the sample in the sample cell, reference in the reference, measure it. And then when you get ready to run your actual spectrum, now you're going to have your sample and the reference. You're going to always subtract this baseline, and that will correct for any differences in those double beam cells. Okay, also, whether you're using double beam cells or single beam, you should always try to put your cell in the same direction. Okay, most cells, when you buy them, they will have a little mark up here on one side called an etch mark. And so you always want to put that mark in the instrument the same way. You know, not one way, this way, and the next time a different way. You always put it facing the same direction. And that's so that the absorption through that cell should always be the same. Because sometimes they absorb a little bit different this way than if you turn them around. Okay, so that's some of the things you should do to take care of your cells. Now, let's talk a little bit more about the baseline or the background. This is actually an extremely important thing to have. So remember, what is your baseline? That's your zero measurement at every wavelength. Excuse me. Ooh, sorry about that. Okay, so the baseline corrects for each wavelength. So we've already seen that it's going to account for small differences in the matched cell, but it also accounts for differences in the power of your source with wavelength. So remember, we said the best source would have a constant intensity at all wavelengths, okay? But they don't. You know, this source is much stronger out here than it is here. So we have to correct for that difference. Your baseline does that. Your baseline also corrects for the differences in the detector response. Now remember, we said a good detector should have the same response for every wavelength, but most of these don't. This one's much more sensitive here than it is at this wavelength. So we have to correct for that. So that's what the baseline does, or the background does. So you always have to run that baseline so that you're correcting for these things. Okay, next, the actual procedure. You have to determine the relationship between the absorbance and the concentration. Okay, and you say, well, I know the relationship. Okay, what is the relationship between absorbance and concentration? Well, it's Beer's law, right? So we said this is the relationship. But remember, we talked about not everything always follows Beer's law. So you actually have to do the measurements. Okay? You have to make a calibration curve. And it's important that your standard and that your sample behave in the same way. Okay? Otherwise, your calibration curve won't be accurate. You have to be careful if your sample contains sulfate or phosphate. These will react with a lot of metal ions and lower their absorption. So it can cause matrix effect problems. So you never want to assume that Beer's law is true, and you never want to use the absorptivity from the literature. You should always do your own measurements on your own instrument. So you're doing them under your own conditions. Okay. And if you have some matrix effect problems, you might need to use standard addition to calibrate for that. Okay, so again, you're going to make a calibration curve. And again, you want to be working between your standards. You know, you don't want to be working out here above your standards or way out here where you might be no longer linear. Okay, so using UV-Vis. We said for qualitative analysis, the uses are limited. Quantitative, widely used. Can measure down to 10 to the -4 to -7, depending on your sample. Okay, but things you have to always consider. You have to select lambda max. You have to be aware of things that might affect the absorption. You have to make sure that you take good care of your cell, that you handle them properly. We talked about running a baseline. You always need a baseline. And then you have to make sure you actually measure the relationship between A and C so that you've got it under the real conditions in your lab with your instrument. Okay, so that's actually doing the experiment. Now, what about some practical uses of it? Well, again, it has a lot of different uses for a lot of different types of compounds. Notice we can do transition metal ions, we can do organic compounds, we can do biological molecules. So most compounds most molecules absorb. So again, very useful method. This is also a powerful method to determine kinetics, the rates, the speed of reactions, because we can measure the absorption over time, and we can watch something forming. Maybe it starts out forming, my mouse, there we go. You get a small absorption and then more, so you can measure the concentration that's forming with time. So very common use for this. It's also used in a wide variety of fields. Now, you don't need to memorize these things, and I'm not going to read them to you. What I want you to see is that this method is used in a lot of different areas for a lot of different types of quantitative analysis. So it's used in clinical chemistry, okay? It's used in biochemistry. It's used in medicines, pharmaceutical. It's used for dyes and inks and paints. It's used in environmental, agricultural fields. It's used for food. And so all of these give you some specifics if you're interested, but just realize widely used methods, a lot of different types of compounds. All right, finally, if you remember back in chapter 1, I told you there were some tables there that just had some useful information. So again, I just want to remind you that those tables are there. So for example, now we've finished talking about molecular UV-Vis absorption spectroscopy. So notice this table tells you what kind of qualitative information do we get and what kind of quantitative information do we get. There's another table that tells you is the method for qualitative or quantitative and elements or molecules. So notice for qualitative, yes, we can get molecular qualitative information. Now it's not a lot, but there is limited. And we also get quantitative. And then the third table tells you the method is not destructive, and we can measure concentrations from 1 ppm all the way up to above 10%. Okay, so just remind you those tables are there if you sometime need to go back and review something about a method. Okay, so that finishes chapter 4. So you need to make sure that you look at all of the homework in the book. So there's no homework to turn in for this chapter, but there are a lot of questions in the book that you need to make sure that you understand. And if you remember, I've already given you the answers to all of those questions. Okay? So you can review the questions and then review the answers that I've given to you. But make sure you understand all of them. Okay, so for the rest of the time, we need to talk about quiz and about future quizzes. So first I'm going to give you the answers to the quiz, and I will post these in WeChat. I've already posted them in Baidu. The first thing you need to know about the quiz answers is that everybody's quizzes are in different orders, and the answers are in different orders. Okay, so I've given you the whole question, but maybe on your quiz, this was question 5 or question 10. So your quiz will not have the same order for either the questions or the answers. All right, so first there was just some multiple choice. These were actually choose one. You only had 2 choices. So simple definitions. So ability to distinguish between small differences in concentration, sensitivity. Using an incorrect procedure is a determinant error. The type of source for molecular would be continuum. Type of calibration curve to correct for instrumental drift is internal standard. Remember, standard addition does the matrix effect. More energy. Different quizzes had either more energy or less energy. You'll have to look at your quiz, but More energy is X-ray and less energy RF. Okay, then there, whoop, wrong way. All right, then there were some multiple choice. So this again was simple definition. Dynamic range is the concentration range over which measurements are reliable. Wavelength selector with the smallest bandwidth, monochromator. Used to determine the relationship between the signal and concentration, that's the calibration curve. True measurement, and then they give you 3 measurements, and then they ask how can you describe the data. So this data is not precise and it is not accurate. You'll notice the average would be very far from this, and these are very far apart. 2 factors, so you had to choose 2 answers. The effect sensitivity, that was the precision and the slope of the calibration curve. Okay, then we had some short answer. So spectroscopy, the interaction of electromagnetic radiation and matter. 3 kinds of transitions, vibrations, rotations, electronic, qualitative analysis. All you had to say was, what is it? Okay, that's all you needed. What material is suitable for a sample holder in UV vis? So either quartz or fused silica. Glass only works in the visible. All right, then we had some calculations, and again, depending which version of the quiz you had, the numbers were different. So that's why there's 2 different calculations here. The procedure was identical. The only thing that was different was the numbers, and one was lead and one was arsenic. So the first one was to calculate LOD at 99%, so you need this formula. So for one of them, it was 0.161. Again, remember units. This one was 0.128. Okay, and then it said, okay, now you have a sample, and they give you the signal for the sample, and they want to know, can you measure this sample accurately? So remember, anytime I ask, can you measure, that's LOQ. If I say, can you detect, that's LOD. So LOQ is 10 plus the standard deviations. So for this one, that would be 0.362. And then the sample is bigger than the LOQ for both of them. So yes, you can accurately measure it. All right, and then finally there was a Beer's law. Again, there were 2 different calculations. Only thing that was different was the numbers. Procedure was the same. So again, this is the kind where you got 2 samples. We have one that's, we know the concentration, then we have an unknown. And remember, the thing that ties those together, the thing that is the same is the molar absorptivity. So the first step is to calculate molar absorptivity. Actually, this one, oh, that's a mistake. This shouldn't be molar absorptivity. This should just be A, because the units are not molarity. So I'll fix that. This should be A for all of these and not molar absorptivity, but same math. So absorbance divided by concentration divided by path length. So this is your absorptivity. And then they gave you T, so you have to calculate A. So remember, this is percent T divided by 100. And then concentration is just absorbance divided by absorptivity divided by path length, and you get this. And notice the units are grams per liter here, not molarity. Okay, so pay attention to units for that. And 3 significant figures. Okay, so those were the absorbance. Again, I will post these answers on the WeChat group so that you have those. Okay, so here are the results for the quiz. Honestly, overall, the results are not very good. This average is probably 10% lower than it should be. So there's really 3 groups of you that I need to talk to differently. So if you got 24 or higher on the quiz, good job. You are doing what you're supposed to be doing. You're studying in a serious manner. You're in good shape. So good job. So that's about a third of you. Then there's about a third of you that, if you got between 18 and 24, that's passing. But quite honestly, this quiz was not hard. In my opinion, there was not one question that was hard on this quiz. So if you're getting, 60, 70%, you're passing, but you really should be doing better. You need to spend more time on this. Okay, and then there are those of you that got below 18, and there's a number of you, and well, honestly, you are not doing anything you need to be doing. That there's no excuse for those kinds of grades on the quiz. You need to get serious. You need to work a lot harder. If you continue to perform like that, you will not pass this class. So there's a lot of you that need to do a lot more work than you're doing. I told you the first day of class, this class has a lot of material. We move quickly, but if you want to pass it, you must demonstrate that you understand the basics. And many of you are not showing me that. So you need to do better, or you will be doing this again. I do not enjoy failing students, but I will. So just be warned, if you do not change your ways, you can do this again next year. All right, now the good news is if you failed this first quiz, you're not ruined. In my class, if you do bad on one quiz, you can still pass with a high grade. This quiz will not affect you if you do better on the future ones, but you're going to need to do much better. Whatever you did for the first quiz, it was not enough, obviously. Okay, so based on that now, there are some issues we need to deal with to try to improve quizzes, and then just also talk about kind of the future for this class. So this class is supposed to be 16 weeks or 32 hours of teaching, and it really does need that much time. And as you know, we already lost one class from the October holiday. We're going to lose another class on January 1st. That's another holiday. And we're actually scheduled to have class on December 25th, which for many of you is an important holiday, and you don't probably want to have class on that day. But quite frankly, I cannot teach everything that I need to teach and lose even 2 classes, let alone 3. So we're going to need to make up those classes that we've lost, or else maybe move the December 25th class if we want to. So I have a plan to help with some of that. So what I'm going to do is I'm going to take the quizzes. Normally I give the quizzes during class time, but I'm actually going to, for the future quizzes, we're going to have those outside of class time. And that will be a way to make up some of this lost time from the holidays. So looking at your class schedule, I would like to have the quizzes on Thursday afternoons. Okay, this was the time for your instrumental analysis lab class, but that class is finished now. So you should all have this time off. This time of day actually works for people in China, and it works for all of you in, they're in Africa or other countries with different time zones. The time is probably the worst for me, but for most of you, this time should be an acceptable time. And that way we can all take the quizzes together. So that is my plan. So for the next quiz, which will be on chapters 4 and 5, I would like to have that in 2 weeks. So next week we will do chapter 5, and then the next week on that Thursday, we will have the quiz at 1:30. Okay, now, if that does not work for you for some reason, you need to let me know, and I will tell you how you're going to do that, okay? So you need to pay close attention to the rest of what I'm going to say. Okay, now, because the last quiz was so bad for some of you, and there are some of you that still do not seem to know how to use RAIN, we're going to have another practice quiz. Now, it doesn't matter what score you get. You don't need to study for this quiz, but you need to take it. Okay, and we're having this quiz so that you can be familiar with the kind of questions and also how to use the system. Okay, there were several of you on the last quiz that did not answer questions in the right way, and we need to try to fix that. The other thing that we're going to change is from now on, the quizzes you're going to take on your computer and not on your phone. This is going to be a requirement from the university for the final exam, so we need to practice that now. It's actually easier to take the quizzes on your computer because you can type in things, you can see things better. It also means that the system can monitor your quiz. You actually have to take the quiz with your computer camera on so that the camera can see you, and you also will need to put in your student ID to do this. Okay, so for this quiz on your computer, everything you can answer in the system. The only time you'll have to take a picture is if you have a calculation. Okay, now on the next real quiz, there will be no calculation. So this practice quiz will be timed, and I'm giving you 45 minutes so you have time to figure out how to use everything. Really, you should be able to finish the quiz in 15 minutes. It's you know, kind of simple questions like the last practice quiz. Okay, and I want you to try to finish this practice quiz by next Thursday, by 9 p.m. China time, so that I can look at the results, and then if there's anything we need to talk about in class the next day, we can do that. Okay, so another practice quiz this week. Now let's talk about some of these details. Okay, so again, the kinds of questions on the practice quiz there'll be multiple choice. Some are single answers, some are multiple choice, multiple answers. The choose one, where you just have two choices. There'll be true, false, there'll be matching, some short answer, and calculations. So on the practice quiz, there's some of each of these so that you can practice, again, all of the forms. All right, so the multiple choice, true, false. The single answer, those where you have many choices, you choose one. Or sometimes there's ones with just two choices and you choose one. Okay, the multiple answer, these are the ones where you have to choose everything that's right. It might be 1 or 2 or 3 or 4 or all of them. And then the true false will be a statement, and you have to mark whether it's true, which means check mark, or false with an X. Okay, so for example, on the last quiz, last practice quiz, there was this question: which animal is the largest? Okay, so some of you were on the last quiz didn't even answer these correctly. So all you have to do in the system is go to whichever one's your answer. Which is the largest? Elephant. Okay, so you click on it and that will be highlighted. Okay, Winter is usually, this is a choose one. Oh, it's usually cold. So again, you click on that answer and it will be highlighted. The true false. Okay, there'll be a statement, the earth is flat. And you know it's true false because it will have a check and an X. So the earth is flat, that's false. Click on it, it gets highlighted. Okay, choose all that are correct. Okay, so anytime there's these ones with more than one right answer, it will say choose all the answers that are correct, or it'll say choose two. So which animals have 4 legs? Well, of course, the dog and the elephant. So again, you just click on those and those will become highlighted in the system. Okay? I don't know why last time some of you were not answering these questions. They're not, just click on the answers. All right, short answer and matching. Now these you don't need to take pictures for. You can just type them into the box for both of these. And for matching, we didn't have this on the last quiz, but we will on the next quiz. So let's review. How do you answer those? So remember, you're going to write a number and a letter. So the biggest animal listed is the. So we look, well, it's elephant. So we would write 1, C. Okay, the smallest animal listed, we would write 2, E. The blank is native to only China. Well, that's the panda, so 3D. The blank is known as man's best friend. Okay, and that's the dog, 4A. And the blank is known to eat humans, okay, 5F. So your answer, you can just type in that box in this form. 1C, 2E. This is how you answer. Don't write the words, don't write the sentences, just number and letter. All right, so on the last practice quiz, what is your favorite season? So this is what it looks like. And so here in this screen, you are just going to type your answer right here in that box. You type whichever one you like. For me, that's fall. Okay, for matching, same thing. You're going to have this box and you're just going to type your answer in the box. So this one. So grass, what color is grass? Well, normally it's green. So we write 1C. Snow, white. 2E. Sun, yellow. 3F. Sky, blue. 4A. And apples, red. 5B. So that's how you answer multiple choice. You just type them in the box on your computer. All right, calculations. You're always going to see these instructions. These are the ones you have to submit by a picture. And remember, for calculation, you always have to have equations and numbers. You always have to have your name and student number. You always have to have units and significant figures. I have to be able to read your answer, and you have to do it by hand. These you cannot type in the box, okay? All right, so calculations are going to look like this. They will always have those instructions. So for this, you're going to write it on a piece of paper. Now, there's going to be 2 ways for you to do this when you have calculations. You can use your phone. You can get into Rain on your phone and do it just like the homework where you attach the picture. You can also attach the picture from your computer. And one of the Chinese teachers actually made a video to show you how to do that. Okay, so this is going to show you in Rain how you can use your phone to upload the picture right onto your computer. And you're going to use this button right here to do that. Okay, so here's the video.
And silently and digitally. Then use your cell phone to take a photo. that, you should the second step, you should go to the Rain classroom and use this button to upload this picture. After press this button, you can see a QR code. Use your cell phone to scan it. Use your WeChat to scan this QR code. Then on your phone, press this button. You can see the plus sign and press this plus sign and select a picture, the picture you take. Then you send it. After that, you can see the picture on your computer and select one. Select this picture, then press this button. Then you will see your picture on your computer.
Okay, so that's one way to get your picture in. The other, again, you can just sign into Rain. All right, so you're going to take this quiz on your computer on Rain. So you need to go to this website. You'll scan the QR code from WeChat. And you still need to use your phone, though, if you have pictures to submit. So again, you can do it according to the video we just saw, or you can sign into Rain on your phone at the same time and do it that way. Okay, now, different on the computer, but we have to do this monitoring. So you're going to need to verify your ID to do that. So the first thing you have to do is enter the class. Okay, so you're going to click on the class, and this will just show you how to do that real quick when you sign into Rain.
And you will send your quiz here. Then they need to verify your ID. Press this button.
Okay, and then here are the steps how you're going to verify your ID. It's actually quite simple, but you need to have a copy of your student ID on your computer because you're going to upload it to the Rain system. Okay, so this video will show you how to do that.
This is the verification of your ID. The first step is to upload a photo of your student card here. So before this, you should have a picture of your student card in your computer, then upload here. After you upload a picture, you should turn on your camera. Here, click here, to turn on your camera and take a photo. Here, this button is a take photo. Then, after you take photo, you can press this button to enter your exam. Then, you can press this to answer your questions.
Okay, so then once you get into the quiz, you take the quiz as we talked about, and then when you're all finished, you can turn it in by clicking, there's a blue button in the upper right-hand corner. So this video is not very clear, but you can kind of see where the button is to turn things in.
You finish the paper, the test paper, you want to turn in, then you can find this button here on the right, upper right. So press this button to turn in your paper. Turn in. And they remind me I still have a one here. They remind me I still have a question I didn't answer. So if you see this, you can press this button. Press this button to continue to finish your quiz. But if you want to turn in your paper, you can press this button here, and here means you successfully turn in the paper.
Okay, so your homework. You should start looking at all the questions for chapter 4. Make sure you understand them. And then you need to take this practice quiz on your computer. Okay, so you're going to need your computer, your phone. You need a calculator because there's one calculation, paper and pencil. Make sure you put a copy of your student ID on your computer so you can upload that. You do not need to study for this quiz. Okay? Remember, the goal is to just practice using the system. The questions are general. They should be easy to answer. Okay? But one question you need to be prepared to answer is you need to tell me, when do I want to have the next quiz? What's the time and date? And then if that's a problem, you need to tell me why. Okay? And again, you need to do this by next Thursday at 9 p.m. Okay? I will, on the WeChat group, I will put the answer to the quiz questions. I will put this part of the PowerPoint about this practice quiz. I will put the 4 videos showing you how to use things. I think for probably half of you, this will be easy. You've been doing fine. You understand RAIN. The rest of you who've been struggling with RAIN, you need to take this opportunity to learn how to use it properly, because there will be more quizzes. There will be a final exam. You have to learn how to use this system. Okay, we will stop there. Our time is up, a little bit past up. If there are any questions, I'll go ahead and stick around, but the rest of you can leave